the area under the BH curve gives, okay, suppose if you have a magnetic material like this and a winding is wounded on this magnetic material, okay, this is a winding, and we have applied a voltage plus and minus terminals. In this way, current will be flown in the winding is I. This is in this direction, okay. Now I is, let us take it as rated. Now from 0 to I, if you vary the current, the magnetic flux density will be increased linearly, okay. That means the flux density and magnetizing force, there will be some domains in this magnetic field, they will align in linear, okay. That is this one. After some time, if you, even though if you increase magnetizing force, that is if you increase the current, what happens, this magnetic material reaches its saturation. That means almost all domains are aligned each other, okay. There are no domains to align each other, that's why it goes into saturation, okay. Then let's take it as B max. Now once if you charge this magnetic material with current I, there will be some residual flux, that is phi r, okay. If you decrease the current from rated current to 0, now this magnetic material curve, that is BH curve, will not follow from this B max to 0, okay. It will follow from B max to like this, okay. If you decrease the current from 0 to I first, that is I to 0, and from 0 to minus I, that means what we have done here is we have reversed this supply voltage, this is minus plus, and now current direction is like this, okay. It will increase up to a saturation will arise. After that, similarly, if you reverse this one, the curve will follow like this, that is minus I to 0 and 0 to I, okay. Now this completes one cycle, okay. That means the area under BH curve gives hysteresis losses per cycle, option B.
Here the question is, an increase in the value of the whole capacitor in the sample and hold circuit results in option A, decrease in acquisition time and decrease in drop rate. Option B, decrease in acquisition time and increase in the drop rate. Option C, increase in the acquisition time and increase in the drop rate. Option D, increase in the acquisition time and decrease in the drop rate. See, if we increase the whole capacitor value, the time constant is going to increase, which will increase the acquisition time, as well as which will decrease the drop rate, means decrease the drop rate. That means option D is correct.
Now in this problem, we have to find the Taylor expansion of sin x at x is equals to pi by 6. Now, Taylor expansion in one dimensional, if f of x is any function at x is equals to a, is given by the formula f of x is equals to f of a plus f dash a into x minus a plus f double dash a by 2 factorial into x minus a whole square plus triple differentiation of f of a by 3 factorial into x minus a whole cube, and so on, somewhere nth term, and so on again. Now here we have to find the Taylor expansion of sin x. So the value of f of x is sin x, and we know the value of a, which is given as pi by 6. Now sin x will be equals to sin pi by 6 plus differentiation of sin at pi by 6 into x minus a, which is x minus pi by 6, plus double differentiation, that is d square by dx square into sin x at x is equals to pi by 6 into x minus a x minus pi by 6 whole square, plus so on. If we simplify this expression, we'll get it as 1 by 2 plus root 3 by 2 into x minus pi by 6 minus 1 by 4 into x minus pi by 6 whole square, plus so on, which is nothing but option 1. Now in this problem, I is given as integral over C cot of pi z by z minus I whole square, where C is the contour 4x square plus y square is equals to 2 in clockwise direction. Then we have to find the value of I. Now, in order to find the value of I, so first what we do is we'll find the residue of the given function. Now, residue of this function will be limit z tends to 1 d by dt of cos of cot of pi z, which is equals to minus pi by sin h square pi. Now, from Cauchy's residue theorem, I is nothing but 2 pi I into residue. We know that residue is nothing but minus pi by sin h square pi, which will be equals to minus pi square 2i by sin h square x, which is nothing but option D. In this problem, we have to find the principal value of minus r power I. Now the given complex number is minus I power I. Now in order to simplify this, first we'll convert this minus I into mod ampere form, which says that e power I theta is nothing but cos theta plus I sin theta. Now, if I take theta as minus pi by 2, then this will become e power minus I pi by 2, and cos of minus pi by 2 is 0, plus I into sin of minus pi by 2 is minus 1. So, e power minus pi by 2 can be written as minus I. So, I'll replace this minus I with e power minus pi by 2 in minus I power I, which is e power minus I pi by 2 whole power I will be equals to e power minus I square into pi by 2, which can be written as e power pi by 2, which is nothing but the principal value of the given complex number. That is option B.
The phase angle difference between primary applied voltage and secondary induced EMF in a transformer is. First, draw the phasor diagram of a transformer. Let us take this as flux. And what will be the applied voltage? Applied voltage, let us take on primary is V1. This will be the V1. And what about induced EMF in primary? Let us take it as E1, and induced EMF in secondary is E2. They both are in phase, but exactly 180 degrees phase shift with respect to applied voltage. Okay, this is 90 and this one is 90. Total difference between applied voltage and induced EMF E is 180 degrees. So option C is correct. So the following is not a self-starting motor. They have given four options here. The option A is single phase induction motor, B is shaded pole motor, C is three phase induction motor. We know that three phase induction motors, they are self-starting. Okay, and in shaded pole motor we can use shaded coils, okay, to make shaded pole motor as self-starting motor. Only here induction motor single phase is not self-starting, so option A is correct.